Welcome to Fun Facts Online. For millennia, humanity's view of the night sky was dominated by a profound yet deeply limiting illusion, the illusion of stillness. When our ancestors looked up, the stars appeared fixed, the darkness between them seemed entirely empty, and the architecture of the cosmos felt eternal. But today, we know the universe is anything but static. It is a vast, furiously expanding theater of creation and destruction. It is governed by invisible forces and populated by billions of unseen worlds. We have officially entered the golden age of cosmic cartography, a transformative era driven by large-scale cosmological sky surveys. Now, these massive observational campaigns are not just snapping pretty photographs of individual galaxies or stars. They are industrial-scale engines of discovery, systematically mapping the heavens across time and space. By harnessing billions of data points, modern observatories are simultaneously tackling two of the most profound mysteries in all of science. On the macro scale, we have the enigma of dark energy, the mysterious force that is literally tearing the universe apart. And on the micro scale, we have the search for exoplanets, alien worlds that may harbor life beyond our solar system. From robotic fiber optic eyes perched on high mountain peaks to next-generation telescopes floating in the freezing void of space, a synchronized fleet of instruments is currently coming online or releasing their very first revolutionary datasets. Instruments like the Dark Energy Spectroscopic Instrument, the European Space Agency's Euclid telescope, the Vera C Rubin Observatory, and the soon-to-launch Nancy Grace Roman Space Telescope represent a total paradigm shift in astronomy. Together, they are rewriting the textbooks on cosmology and planetary science as we speak. So let us dive right in and start with the dark energy enigma and the massive cracks currently forming in our standard model of the universe. To truly understand the scale of the dark energy problem, we have to look back to the late 1990s. Astronomers were meticulously measuring the light of distant, exploding stars called supernovae, and they made a terrifying and beautiful discovery. The expansion of the universe was not slowing down under the inward pull of gravity, as everyone logically expected. Instead, it was accelerating. The driver of this acceleration was dubbed dark energy, which, if we are being honest, was really just a placeholder term for a profound state of scientific ignorance. In the standard model of cosmology, known as lambda CDM, dark energy is treated as a cosmological constant. Think of it as an unchanging, intrinsic property of space itself. The idea is simple. As the universe expands, more space is created, and therefore, the total amount of dark energy increases, pushing galaxies apart ever faster. For a quarter of a century, this model held firm, but today's precision sky surveys are putting that constant under unprecedented stress. Enter the Dark Energy Spectroscopic Instrument, or DESI for short. DESI is mounted on the Nicholas U. Mayall 4-meter telescope at the Kitt Peak National Observatory in Arizona, and it is an absolute marvel of optical engineering. Instead of a traditional camera, its focal plane is equipped with 5,000 robotically controlled fiber optic cables. Picture this. Every single night, as the massive telescope points to a new patch of sky, these 5,000 tiny robots swirl into position in a complex mechanical dance. They align perfectly with the incoming light of 5,000 distinct galaxies and quasars, all at the exact same time. By analyzing the spectrum of light from each object, basically reading the light like a cosmic barcode, DESI precisely measures its distance. This allows scientists to construct the largest and most incredibly detailed three-dimensional map of the universe ever made. In March 2024, the DESI collaboration dropped a bombshell on the physics community with its Data Release 1. By tracking how matter clumped together over the past 11 billion years, they used a metric known as baryon acoustic oscillations. You can think of baryon acoustic oscillations as frozen sound waves from the dense plasma of the early universe. Imagine dropping a stone in a pond, and right as the ripples spread, the pond freezes solid. DESI is essentially measuring the distance between those frozen ripples to see how the universe has stretched over time. What DESI found was that the expansion rate didn't perfectly align with the cosmological constant. When combined with data from the cosmic microwave background and supernovae, the results showed a stunning hint. Dark energy might actually be weakening or evolving over time. Fast forward to May 2025, and DESI's Data Release 2 amplified this seismic shift. Utilizing a staggering 14 million redshifts, which is more than double the data of their first release, the survey provided even stronger evidence that dark energy's equation of state is not strictly constant. The data suggested that the energy density driving the universe's expansion may have actually peaked at a redshift of 0.45 and is now slowly decreasing. While the physics community rigorously awaits the gold standard 5 sigma threshold for a definitive, undeniable discovery, these observations, currently resting around a 3 to 4 sigma confidence level, have definitively cracked the foundational lambda CDM model. If dark energy is indeed a dynamical fluid or field rather than a constant property of the vacuum, the ultimate fate of the universe is completely up for debate. Whether everything ends in a big freeze, a violent big rip, or a collapsing big crunch is no longer settled science. While DESI works tirelessly from the ground, the European Space Agency's Euclid telescope is tackling the dark universe from the void of space. Launched in July 2023, Euclid was specifically designed to measure both the distribution of galaxies and the subtle warping of their light caused by dark matter. This phenomenon is known as weak gravitational lensing. By February 2024, Euclid had begun its grueling 6-year main survey, aiming to cover 1/3 of the entire sky and catalog billions of galaxies. Its capabilities were breathtakingly demonstrated in May 2024 with its early release observations, and further cemented in March 2025 with the monumental Q1 data release. The Q1 release alone mapped an unprecedented 63 square degrees of the sky in immaculate high-resolution visible and near-infrared light. That is an area 300 times larger than the full moon, mapped in spectacular detail. Euclid's images are a masterpiece of cosmic depth. Take its observation of the Abell 2390 galaxy cluster located 2.7 billion light-years away. In a single frame, Euclid captured more than 50,000 galaxies. The massive gravitational bulk of this cluster, which is completely dominated by invisible dark matter, acts as a massive cosmic magnifying glass. It literally bends and curves the light of background galaxies into luminous arcs and stretched-out streaks. By systematically mapping these funhouse mirror distortions across the entire sky, Euclid will allow astrophysicists to trace the invisible scaffolding of dark matter that dictates exactly where galaxies form and measure how dark energy has stretched that scaffolding over the last 10 billion years. Yet, large-scale cosmological surveys like this inevitably become absolute treasure troves for other disciplines. During its early observations, Euclid not only hunted for dark energy, it stumbled upon hundreds of new dwarf galaxies, surveyed massive star-forming regions like Messier 78 with unprecedented infrared clarity, and discovered a multitude of free-floating rogue planets. These are incredibly lonely worlds, entirely untethered to any star, drifting blindly through the freezing galactic void. This beautifully illustrates the dual nature of modern sky surveys. A wide-angle lens meant to capture the vast architecture of the distant cosmos naturally captures the wandering planets right in our own backyard. Now, if Euclid is photographing the static architecture of the cosmos, the Vera C. Rubin Observatory is filming its blockbuster action movie. Perched high in the dry, thin air of the Chilean Andes, the Rubin Observatory represents the absolute pinnacle of ground-based optical astronomy. At its heart sits the legacy survey of space and time camera. This is a mind-boggling 3.2 billion pixel digital sensor, making it the largest digital camera ever constructed in human history. To display just one of its images at full size, you would need hundreds of high-definition televisions. On June 23, 2025, Rubin released its highly anticipated first light images, capturing the Virgo galaxy cluster and the radiant Trifid and Lagoon nebulae in astonishing detail. The Virgo cluster image alone, composed of over 100 overlapping exposures totaling 3 trillion pixels, encompassed roughly 10 million galaxies. Yet, this was merely a static preview. The true, world-changing power of the Rubin Observatory lies in its temporal resolution. When its 10-year survey fully commences in 2026, Rubin will photograph the entire visible southern sky every few nights, generating a high-definition, decade-long time-lapse of the universe. On February 24, 2026, the observatory gave the world a taste of this dynamic capability when it launched its alert production pipeline. In a single night, the system fired off 800,000 automated notifications to astronomers worldwide. It flagged celestial events that had changed brightness or position since the last observation. Once fully operational, it will generate up to 7 million alerts per night. Through this relentless optical sweep, Rubin is expected to discover millions of transient events. We are talking about supernovae exploding in distant galaxies, tidal disruption events where supermassive black holes literally shred wandering stars into spaghetti, and the rapid flickering of active galactic nuclei. But closer to home, Rubin's massive field of view is revolutionizing our understanding of the solar system and the local stellar neighborhood. In early 2026, the observatory spotted 2025 MN45, a 0.4-mile-wide rock that completes a full rotation every 1.88 minutes. That makes it the fastest-spinning large asteroid ever found. By cataloging millions of near-Earth asteroids, Kuiper Belt objects, and stellar phenomena, Rubin provides the ultimate dataset to finally bridge the gap between abstract cosmology and local planetary science. While surveys like DESI, Euclid, and Rubin have fantastic secondary benefits for planetary science, the upcoming Nancy Grace Roman Space Telescope is explicitly designed to conquer both dark energy and exoplanetary astrophysics at the exact same time. Named after NASA's first chief astronomer and the mother of Hubble, the Roman Space Telescope successfully completed its structural assembly in a massive cleanroom at NASA's Goddard Space Flight Center in November 2025. Scheduled to launch on a massive SpaceX Falcon Heavy rocket as early as the fall of 2026, Roman will carry a 2.4-meter primary mirror. That is the exact same size as the legendary Hubble Space Telescope. However, thanks to its cutting-edge wide-field instrument, a 300-megapixel infrared camera, Roman's panoramic field of view will be 100 to 200 times larger than Hubble's. It will capture the same staggering, beautiful depth of the universe, but across vast swaths of the sky in a single exposure. Roman is perfectly poised to complete the exoplanetary census begun by the legendary Kepler Space Telescope. Kepler revolutionized astronomy by proving that there are more planets than stars in the Milky Way galaxy. It did this primarily using the transit method, where scientists watch for the minute, barely detectable dimming of starlight when a planet crosses in front of its host star. However, Kepler was mostly sensitive to large planets orbiting extremely close to their stars. Roman is going to push our planetary search to the outer limits, using a technique perfectly suited for a wide-field cosmological survey: gravitational microlensing. This incredible phenomenon occurs when a foreground star passes directly in front of a background star from Earth's perspective. The gravity of the foreground star acts as a literal lens, temporarily magnifying the light of the background star. Now, if the foreground star has planets orbiting it, those planets add their own tiny, distinct gravitational warps, creating a secondary spike in the magnification. Because microlensing does not rely on capturing the actual light from the planet or the host star itself, it is incredibly sensitive. Roman is expected to continuously monitor hundreds of millions of stars toward the galactic center, discovering thousands of exoplanets in the process. Crucially, microlensing is sensitive to planets orbiting far from their stars, like the cold gas giants and ice giants, as well as rocky, Earth-sized planets that previous missions simply struggled to detect. It will even find hundreds of those rogue planets wandering the dark space between stars. Furthermore, Roman carries a revolutionary coronagraph instrument. This is a highly complex system of masks, prisms, and deformable mirrors that uses destructive optical interference to physically block out the blinding glare of a host star. Think of it like putting your thumb up to block the sun so you can see a bird flying next to it, but engineered to atomic precision. By cleanly separating the planet's faint light from its blinding star, Roman will allow scientists to analyze exoplanet atmospheres, eagerly searching for the chemical signatures of habitability. What makes this 2024 to 2026 era of astronomy so historically significant is the profound, beautiful convergence of these disciplines. Historically, a cosmologist studying the accelerated expansion of the universe and a planetary scientist searching for habitable worlds operated in totally different academic silos, using completely different instruments. Today, the very same data streams are fueling both fields. The physics of general relativity is the ultimate thread, tying it all together. The weak gravitational lensing used by Euclid and Rubin to map dark matter and constrain the evolution of dark energy is the exact same physical mechanism, just scaled up, as the microlensing Roman will use to find Earth-mass exoplanets. You simply cannot map the distant universe without looking through the foreground of our own galaxy, and in doing so, the local and the universal become deeply intertwined. Moreover, the sheer volume of data produced by these observatories has necessitated a complete revolution in computer science. The 270 terabytes of data from DESI DR1, the millions of alerts generated nightly by Rubin, and the massive infrared panoramas from Euclid and Roman simply cannot be analyzed by human eyes alone. Artificial intelligence and deep neural networks have now become standard astronomical tools. Over 50% of the scientific articles published alongside Euclid's Q1 data release relied entirely on AI to classify galaxy morphologies and infer merging tidal tails. Additionally, citizen science platforms like Zooniverse are stepping in to help crowdsource discoveries, inviting the general public to comb through Rubin and Euclid's data streams to spot asteroids, supernovae, and peculiar galaxies that the algorithms might miss. We stand on the precipice of a fundamentally new understanding of reality itself. The early returns from DESI suggest that the dark energy pushing our universe apart is not a monolithic constant, but a shifting, dynamic force. This is a revelation that, if confirmed, will shatter the standard model and require a complete rewrite of modern physics. Euclid is successfully rendering the invisible dark matter webs that dictate cosmic structure into stunning, tangible visual catalogs. The Vera Rubin Observatory is currently awakening, preparing to stream a live, 10-year cinematic record of the rapidly shifting heavens. And the Nancy Grace Roman Space Telescope sits in a clean room, fully assembled and waiting for its fall 2026 launch to peer deep into the infrared void, ready to image the atmospheres of alien worlds while simultaneously tracing the expansion history of the cosmos. To map the sky is to map our origins and our destiny. Through the combined power of these massive cosmological surveys, we are tracing the universe from the absolute largest scales of dark energy acceleration all the way down to the smallest rocky planets drifting quietly in the galactic night. The static night sky is gone forever, replaced by a living, breathing cosmos that we are finally, truly learning how to read. Thank you for joining me on Fun Facts Online. Never stop looking up, and I will see you in the next deep dive into the wonders of our universe.